That's it. Okay, good morning. So I'm going to restart sharing my screen. This is it, I suppose. And then, okay, I was already sharing. Okay. Right. So, good morning, everyone. We are starting the theory aspects of cloud computing and big data. I will assume that not all of you are sharing both courses, so I might repeat some of the things that we went into the last session, and I mean the first laboratory session, but I hope that you will be patient and that those that have already listened to some of the instructions, will be patient and accept the listening to a kind of repetition. So, as you can see, the Blackboard is more or less ready. By next week, all the material that I am sharing in the external website of the course and the laboratory will be also on Blackboard. But I remind those that didn't attend the laboratory session that all the material, including the slides and the videos, will be online, so that for some reason you do not attend or you arrive late, etc., you can have access to those, okay? And I also remind those that haven't joined the Slack already that the Slack is a very practical way of interacting, because we can interact asynchronously and out of the course at any time. So please feel free to say hello, to ask questions, to share things that you find out. It's a working group, and the idea is also to have interaction beyond the official course sessions. I am also going to ask you if you have questions to raise the hand, but feel free to open the mic and interrupt me, particularly because I am really kind of struggling with Blackboard, so I'm not sure that I will see the raised hands or people asking questions on the chat. So please feel free to open your mic and interrupt if you have some questions. So let's start with theory. In fact, this is something that you might have seen earlier. The idea behind cloud computing and big data today is a kind of trend that has emerged not in computer science, in fact in social sciences, that is called datification. And the slogan of this datification story is that because of the evolution of technology, where we can produce data and collect data in many different conditions, the idea is that we are sensing reality, things in reality that we haven't sensed before. Okay, and so the idea is that data is everything, and everything is data. And this opens a great change in the kind of ways we can process data, and we can get something out of data. We can exploit data, okay? And the two leading elements that make this possible is, of course, the big data trend that, as we discussed previously, has emerged some years ago. And then since we are increasing the scale at which we have to deal with data, there are specialized architectures well adapted in order to face this scale, and this is part of the cloud computing trend. Okay, so these both cloud computing and big data are the two columns on top of which it is possible to talk about datification today. And this is the motivation, at least for the content of this course. We are going to try to see which are the tools that we have available as computing engineers in order to build systems that will make this datification reality. So if we have the right definition of datification, the idea is that we are going to render into data aspects of the world that have never been quantified. Of course, you are aware today because at the end or the beginning of the end of last year or the beginning of this year, Facebook, for example, came up with this Meta Universe project. And there, the idea is exactly this: how to figure out to get and collect all data possible from reality in order to reproduce a virtualized reality on top of which we can reason, we can exploit, we can play, we can learn, we can everything. Okay, so we are rendering reality into data and the parts of reality that haven't been sensed before. And then what is the objective? Well, the objective is that any individual, which is a big change with respect to previous uses of modern technology, is that any individual can analyze these huge amounts of data in short periods of time in order to obtain analytical knowledge of the reality of the context that has been sensed. And to do what? Well, in particular, in order to promote evidence-based decision making. Okay, so this is an important movement of the cursor with respect to the way many strategies, decision-making strategies, have been done before. Let's take an example. Let's take politics as example. If you were a politician of the old school, what you did is you tried to figure out which were the expectations of civilians, and you yourself as a civilian, you could imagine which were your requirements in terms of traffic, in terms of services, public services, for example. And then you made decisions telling people, okay, we are going to build some hospitals, we are going to build a bridge, we are going to extend the roads because traffic is becoming complex in the city, and so on and so forth. The idea, if we go to the new way of thinking, is that you are going to really collect data from traffic, from the way people move, the way people evolve within the urban spaces, and out of that, you are going to promote an execution plan, a political plan that will be based on the evidence, concrete evidence of what you have observed out of data. Okay, so it's no longer empirical, it is based on clear observations of specific behavior of your civilians, and then you figure out how to respond to the requirements. Okay, and this happens also in our cases. For example, if you are the CEO of a computing, of an IT center, you are going to collect different data from your users, from the machines, from the network, and then you are trying to make decisions whether to buy new servers, whether to connect, extend the bandwidth in order to execute some processes, you see, but not in an empirical manner, but in a data-based manner. And this is the objective of datification. And then, of course, you have guessed, because you have had already enough experience in the construction of systems that there is a lot to be done, because you have to figure out whether your collected data is complete, the quality of your data, etc., etc. And so the challenge for us as computing engineers is are we going to build reliable systems that can exploit data in order to support this database decision making. So depending on the way we are going to use the data, in fact, there are different methodologies in order to define strategies. And these methodologies come from experimental sciences. The experimental sciences themselves have also evolved thanks to these possibilities of datification. And today we have different experimental sciences that are devoted to attack the different problems that will exploit data in order to develop some solutions. And here are some examples of them that you probably have heard about. That is, for example, social data sciences, where the idea is to see social phenomena as observations, and then the idea is to figure out how these social phenomena can be studied and understood. Okay, example of these social phenomena, for example, our behavior with respect to playing games online, for example, the phenomenon of people being locked down during the pandemic, these kind of things. So the idea is that social scientists collect the data and then they apply evolved social sciences methodologies in order to study the phenomena and then drive conclusions out of their observations. There is also network science. Well, there you have guessed that all social networks have provided enormous social networks that can be observed and analyzed in many different perspectives. There are others like digital humanities, where again the idea is to solve problems that have been addressed manually in the study of humanities. And there are other sciences, like, for example, computational science, where the idea is to evolve mathematical methods in order to use this data and open up new possibilities with respect to mathematics. The common aspect of all these sciences is that the backbone of them is data, okay? The idea is that there are data collections that enable setting and conducting experiments in order to drive hypotheses and lead to valid conclusions, models, simulations, and understanding. So with respect to your previous experience in the way you exploit data by querying, this is the next step that we do when we query data, okay? We are no longer looking for information. We are using data in order to drive models, understanding, knowledge, okay? And this is a way of querying, but with a much more ambitious objective. And well, what do we do as computing engineers with respect to this? Well, the idea is that we have to develop methodologies that are going to weave data management, greedy algorithms, and programming models, and all of them have to be tuned and deployed in different target computer architectures in order to drive solutions. Okay, so it's as I said in the session of the laboratory, it's like going back to the beginning in terms of your education, and we start having a look at the algorithms, having a look at the knowledge you have regarding data structures and systems design, and put them all together in a new context. And the context is scale, is greediness, is new programming models, and sui generis architectures. Okay, so this is the whole challenge of driving all these together, and this is the challenge that we are going to address in this course from the theoretical aspect, and then of course the associated laboratory in a more practical perspective. What are the applications that are driven by this kind of context? Well, there are a lot. And this is what is interesting and important with respect to having a course like this at the final step of your education. Now, the idea is that, of course, these are examples of applications, but that you figure out the next applications, those that do not exist, in order to have a nice professional perspective and career. Okay, so the idea of our career in particular is that the more we invent new kinds of applications, the better we are going to be inserted into the professional arena. Okay, so this is what behind all these exercises, this is what you must expect from the course. Okay, so examples of applications: business networks, understanding the behavior and the requirements of people, for example, regarding the books they read, the films they enjoy, the food they eat, their physical activity, the way they purchase, the way they consume, the way they behave when they are driving, and so on, and then provide applications that will let these people have a new experience with respect to what they have been used to do. Another example is, of course, you have seen, because it has been here for a while, this haptic, for example, interfaces. With this story of metaverse, the more and more we will see these haptic interfaces collecting data from the brain and from the different parts of the body in order to reproduce the way people feel, and then try to provide them with new experiences when they play, when they learn, etc. So this is a kind of applications that are like the right clients of this adaptification phenomenon, and then of course of the type of architectures that are associated to what we call in general the cloud. What do you, the good news is that depending on your interests, depending on the philosophy of and the way of you want to organize your professional career, you can decide whether you are more devoted in order to address requirements from business, from social for good, for medicine, etc., astronomy, whatever. Okay, so the idea is to have the right underlying knowledge and infrastructure, mental infrastructure, in order to address the kind of applications that I have enumerated, and according to your personal interests. Now, if we try to zoom in into the kind of things that we have to do in order to make this concrete, well, there is, first of all, the need to profile what we call data, okay, in this kind of context. As I said before, the big data trend has been around for more or less 10 years. So it's not longer a buzzword. It's no longer something new. It's something that is there and that has already produced some results. And there are lessons to be learned out of the experience of having this trend emerged in computing science. And the lessons that we can get out of this trend is the possibility to associate properties to the data we collect. And these properties are those that are going to guide which type of computing resources we need in order to exploit such data collections. Okay, so first thing that I want to underline is note that I'm not longer talking about databases. Okay, I'm talking about data collections. Okay, so set of observations of data from many different types that are available, that are digitalized, of course, and that are available somewhere on the net. Okay, and there are five main properties that us as people that are going to exploit them must consider. Of course, the one that is the most obvious one, because it's the summit of the iceberg in a way, is volume. Okay, so it is not a question of how big a data collection is. The question is how big, of course, the size, but also the perspective in which the size will grow to some extent, and what this volume, this size, has to do with respect to two main aspects that we have to consider in order to deal with it. The first thing is, where are we going to archive it and for how long? And the second thing is, what type of algorithms are going to use this data so that it can be handled in these active and running processes. Okay, so how much main memory do I need in order to put this data available to programs that can exploit this? Okay, and why is it important? And we are going to assume that even if we are going to go beyond the limits of the systems that we know, the idea is that if for some reason, for some application, we need to go beyond those existing types of resources, we can invent them or develop some research and development in order to have this support. But at least we have to characterize this volume with respect to the resources we require. Okay. I don't know how much professional experience you have. You might have had internships in some companies, but some people, when they come to you and ask for the development of a system, they say, I have a lot of data and I'm dealing with big data. And this is something that you have to be careful about. It is not because you have an important volume of data and that you do not have the right machines to process it that you are dealing with big data. Okay, this just says that you are poor in resources and that you cannot have the right machines in order to deal with your data, but that has nothing to do with big data. Okay, big data, and when we really talk about the huge volumes of data, is those volumes that really drive you to the limits of the possible computing capacity that we know in history to be used in order to develop your systems. Okay. So anyway, the first characteristic and the most evident one is, of course, the volume. Then you have another important aspect that is related with the volume, which is velocity. The question is not that I have a lot of data, is how often does this data, those new data, is produced. Okay, so velocity describes the pace at which data is produced. And this is more challenging than dealing with big volumes, because this means that there will be streams of data arriving to some system, and these streams that might be continuous have to be dealt in a continuous manner. Yet, as you remember from discrete mathematics, the type of machines that we normally use in order to process data are discrete. They are not continuous. And so I have a kind of impedance mismatch between the fact that I'm producing something in real time continuously and that I have to process it in a discrete manner. So the idea is that I have to figure out some strategy in order to have the illusion that I'm dealing with this data continuously, even if in fact I am processing it in a discrete manner. So velocity is, I have to be aware of the pace of production so that I have the right strategies in order to process these continuous streams as if I had a real-time system and not a discrete system. Okay, and this is also an example of the way these famous big data drove the computing architectures to their limits, okay, because of this characteristic of discrete versus real-time production. Then, do I have questions? I think I don't. Remember, you can open the mic at any time. The other aspect is variety. Since I'm talking about different technology producing data, of course, different technology means different formats and different representations of the data. And what we learn in the fundamental education of data management is that if I have a lot of diversity, if I have heterogeneity in terms of data, the right manner to deal with it is having a pivot representation. This comes from mathematics too. Okay, I have a pivot representation. I transform everything into this pivot representation, and then I operate. The problem is that I have volume and that I have velocity. So there is no time. And there are also a lot of resources to consume if I do these transformations, okay? So the idea is that with respect to variety, I have to accept variety and then figure out how to deal with it in a lighter manner and not through transformations because they cost a lot in performance and in money. Okay. Fourth aspect to consider is veracity. When you had your course on fundamental databases, you were taught that consistency is maybe one of the most important characteristics that your database must have. And there are formal norms and there are transactional models that help. There are triggers, functional constraints, etc. And all these mathematical and computational mechanisms are devoted to keep the database consistent with respect to some specification. In this context, this is no longer possible because there is not just one way of associating consistency to data. There are many possibilities of consistency with respect to the observations we collect into these data collections. I always use the example of sensors, for example, used to sense a temperature. If you have a room and you install your sensors in different parts of the room in order to estimate the temperature of the room, in fact, the readings that you will obtain from each sensor will vary. Okay, if some sensors are close to the window, they will sense some temperature, which can be lower or higher to the temperature you have in a place where there is no air, or it's too closed, or you have some appliances producing heat. And if you see the readings, you will have these changes in the observations, but all the observations are right. Okay, so they are consistent with respect to the reading of the temperature according to their location, but they differ and all refer to the same room. Okay, so this kind of problem in terms of veracity comes up constantly when we deal with these data collections coming from reality. Okay, and the idea is that we have to accept these changes of veracity and figure out again how to deal with these changes and these not a global truth about the data. And then the fourth characteristic is value. In fact, data has an associated cost, and the cost is determined, for example, with respect to the architecture, the technology that is used to collect it. It also has to do with the way it is maintained and archived. It has also to do with the provenance of the data. And this economic value has its importance in all the way and all the strategies we are going to use in order to process our data. Again, I often use things that we already see in our normal life. I might be sure that you all use streaming providers to access music. This is the subscription that we pay or the cost of a song that we buy, for example, in platforms like iTunes. This is the economic value associated to the data, which in that case is audio. Okay, so the question is how to estimate the value of the data and then how to integrate this economic value into the whole exploitation of data collections. So these 5 properties are the first guiding properties that we have to deal with when we are talking about data in terms of datification, exploitation, etc. Okay, and there is a project and a vision of data in the way it will grow in next years. And the idea that you can see here is that people think that we will need new units in order to measure the data that we will have to deal with in future systems. And we talk about jottabytes, thousands of jottabytes, which are called brontobytes, and thousands of brontobytes that are called geobytes, which will be the normal units that we will be dealing with in our classic systems. Okay, and of course this will imply having new architectures that will really be able to normally deal with these units of data. Okay, so quite beyond what we are dealing with today. Now, as I said, the challenge of having these data collections, big data collections, is of course storage. Where are we going to store all this data? Where, for example, think about Facebook or about Twitter. They store all our posts that include images, etc. And this information and this data is sometimes stored beyond our physical lives. Okay, so where does it reside, and how much can it really evolve? Well, as I said, well, you have these different data collections. Here I have those that are normally use today. And the idea is that on the other side, we have the right storage supports that can deal with the data. And in fact, what it's important to retain, particularly with respect to this course, but in general with respect to any application that can be built today, is that we have to deal with a spectrum of storage support that lies on behind any application. So of course we have normal disks, we have to deal with RAIDs, so farms of disks, and there is new architectures like the cloud that provide farms or of disks where we can put our data. This again is something that you are quite used to see if you are Dropbox users. This is the case. There are some farms of disks lying somewhere in the world, and they provide you with some space in order to deal with your data, and it is reliable, etc. So it is duplicated so that they can ensure availability at any time, and then rely in these kind of architectures. And the question, if you want to state the problem in a theoretical manner, is that out of different collection sizes, the decision-making objectives that we have to deal with is where are we going to store our data on top of this different spectrum of data. Example, if you are Dropbox users, what is the data that you accept to put on the cloud, on Dropbox, and what is the data that you keep local in your machine, and what is the data that you accept to have a mirror on your local machine? Well, normally, since communication, since connection sometimes fails, very critical information, we tend to have it locally, either in a mirror of Dropbox or really a copy on our computer or on our cell phone. Okay, why? Because we consider that if anything goes bad, particularly connection, at least we have a copy of this critical data available. Okay. If you are a government, of course, that what will you decide? Well, critical data about the country, you might accept to have it on RAIDs or on cloud-like solutions, but ensuring that the data centers that are behind these architectures reside in your country. Okay, so you see there is the technical, there are the technical aspects of decision making that play a role, but there are also these contextual requirements that help to decide which data goes where. Okay. If you are, for example, willing to have availability, ensure availability, you might accept to distribute and replicate the data in many different servers, because if your machine goes bad, if your cell phone is stolen, for example, then you are sure that you will have a copy somewhere as backup in order to be able to access your data. Okay, so all these elements will play a role in order to decide the right strategy in order to store your data. And then, with respect to storage, there are two elements that have to be considered. First of all, of course, you have the data in some format. But then if you want to exploit the data, normally you have to use a logic data model in order to have its representation. And the idea is that you are going to accept different formats and different data models in order to represent your data. And then you have to decide which are the properties, the guarantees that you want to associate to some portions of the data. For example, if you know that there will be many users accessing to the data in write mode, well, then you have to ask a system managing your data to ensure concurrent control in order to be sure that you will not have dirty data, dirty readings when someone else is accessing to the data. And if you have some specific restrictions with respect to a specific level of consistency, see that I'm talking about level of consistency and not of general consistency. So if you want to ensure some level of consistency, then you have to ask the guarantees that will ensure that this consistency is respected despite the data being modified by many users. So this panorama of storage support has to be considered when dealing with any collection of data with any of the properties that I have enumerated in the previous slide. But there is maybe something much more interesting than these strategies, and there are two characteristics when you have to think about data storage. The first one is the one that we know from the beginning of our studies and even before, is persistence, okay? Persistence, remember, that describes the fact that data survive to the execution of a program, okay? But the execution of a program, the life cycle of a program is very short, okay? So the challenges are less important, but anyway, they are. So, and then you have the second kind of storage, which is permanence. For how long do you want your data to be stored in some persistence support? Okay, and this changes everything because in my example of Facebook, can you imagine the number of users producing continuously data? Where are they going to store the data? Well, of course, there is a requirement of new technology that should go beyond the kind of technology that we know. And those that are interested in these storage issues, for example, today there are solutions based on crystal and based on DNA that are quite well adapted, for example, to deal with cold data. Okay. For example, for those users on Facebook that pass away, you might ensure that their data will be permanent, but since they are not really quite used and they move not very much, so you might accept to store them, for example, on DNA support. For those that haven't heard about DNA, the idea is to use biological elements in order to store the data. Some very popular ones that are being published already, and there are companies already using them, is with milk. The idea is that you are going to use the DNA of milk in order to store your data. Okay, and so there are you can have, for example, the quite a bunch of yottabytes or petabytes in a liter of milk, and you store it on refrigerators. Okay, so you have your bottles of milk containing your data. Okay, this is something that is running already in some companies. Others rely on crystal. So the idea is that in a very small device, you can store a lot of data, which is interesting because of the volume of data that you can store on this kind of support. But it's also very interesting because the energy required in order to store the data in this kind of support is very low. Okay, so you do not use a lot of energy and you can store a lot of data. So these kind of solutions are related both to persistence and to permanence. So you as computer engineers, you have to decide both, of course, the size, how big is your data collection in order to decide the right type of disk in order to store it, whether it is used continuously or whether it is cold, for example, and also for how long do you want your data to be permanent, okay? And also because, as you know, the formats evolve and the physical characteristics of the support evolve, and from time to time, if you really want your data to be permanent, you have to transform them in order to be sure that there is the right technology in order to exploit it. So you have this very hardware issues, but that are not far away on the decisions that we have to make as computing engineers in order to develop the right strategies in order to store our data. And then you have, of course, the functional architectures, which are the right systems, the management systems that will accept, run on top of this kind of technology, and that have to be deployed, as I insist, in many different architectures. During the course, we will see that cloud is a family of architecture, in fact, okay? And that also parallel systems and clusters, etc. This is just the name of a family, and there you have many different instances of these generic concepts that have to be considered in order, as I said, to develop the right management and exploitation solutions. And this is what we're going to study in this theory aspect of cloud computing and big data. Okay. Of course, we will not use, for the time being, we will not use DNA supports, etc. So we will use the kind of solutions that are in the market today, but we will also learn which are the associated perspectives that are running already, that are of access of academy for the time being, and that I'm sure that you will, with high probability, will have to use in your professional life. Okay, so with respect to the functional references, the question that we will be asking is which are the right management operations in order to deal with this kind of data collection with these properties and in these different architectures. Okay, so this is the overview of the ambition of the course. Sorry. So here you have if we are talking about permanence, there are, of course, descriptions, technical descriptions of the expectance, the life expectancy that you can associate to data residing in this persistent support. As you can see, for the time being, classic solutions like optical memory ensure 10 to the 20 years of permanence. Okay, so beyond that, we would have to develop some strategies in order to maintain this cold data, this stored data, and be sure that others can use it and exploit it later on. Now, with respect to, so we go from disk, now let's have a look on computing capacity, CPU cycles, okay? So CPU has evolved in a very important manner, and today there are many different devices and chips that have different characteristics with respect to the way they will run these cycles. Okay, so what we learned in our basic education in computing is, of course, machines that rely on CPUs, where the CPU relies always on a cache. This is the physical cache, okay? I'm not talking about the cache used by the DBMS, the physical cache of associated to our machines, and of course the main memory. And this is what we call a node. So our computer is a node that includes computing on some CPU or many cores of CPU that have their own cache. They are all together associated to main memory, and then we can expect some performance with respect to that, and that is something that we are quite used to reason about, because we buy our machines with respect to these three characteristics. So the decision that we make, if you are gamers, for example, of course you need a lot of computing resources, etc. So you have to make sure that your machine will resist processes which are online, which require a lot of rendering, etc. No? So, but anyway, the decision making that you are going to do with respect to the machine you buy, well, it's with respect to this. Then, of course, in fact, what we use today is kind of this. It's multiple CPUs relying on the same memory space, and with a cache global to the machine, and a cache associated to one or several cores, depending on the architecture we buy. Okay, so this would be classic ones that, you know, at the beginning of this century started to emerge, and this is what they are used. Then, because of many different requirements, CPU has its limits, and so vendors have developed elements that that can have much more computing capacity. One that you might probably know already is GPU. GPUs are very common in machines that need visualization. Okay, so visualization is a very greedy process to run, and these GPUs were developed in this. You might have heard about the company NVIDIA, which is one of the main vendors of this kind of solutions. So the idea here is that you have these accelerators. There we will have some experience in the laboratory with the use of this, because today many cloud vendors enable you with the access to GPUs in order to nothing to do about visualization, but in order to run greedy algorithms that exploit data. Okay. And so, well, there are these GPUs, but well, then you can have systems only using GPUs, or you can have hybrid versions where you have CPUs and GPUs, and then the challenge is how to cope these different elements, electronic elements with different characteristics, so that the whole system will run in a very performant manner, and that the processes will really exploit all the capacities of your system. Of course, if you want to state the challenge of the game here is how to exploit as much as possible in an optimum way all the CPU resources, the computing cycles resources that you have in your machine so that your processes will run in a very performant manner. And of course, then you can move into computers which are called high performance computing architectures. There you are moving into data centers where you can have, sorry, my iPod is going out of my ear. Okay, so you can have these centers where you can, that are really devoted to run greedy processes in a very fast manner. You that are in Puebla, well, now you are locked down, but there is at some point in Mexico's history, there was an initiative in order to develop high-performance computing centers. There is one in Puebla, which is the laboratory of the southeast region of Mexico. It is hosted at BUAP, but there is a node running in UTLAP. Okay, so these kind of centers are available. There are many in Mexico, and so these kind of centers adopt these high performance computing architectures in order to run greedy processes. And then, of course, depending on the way you grab this high performance computing capacity, you can have HPC centers, or you can have cloud solutions that are intended to go beyond the kind of services that you can access with HPC centers. Okay, so of course here in the course it will be important that we will make the difference between these two kinds of solutions, because this is a very classic misunderstanding with respect to architectures. People, there is a confusion between high performance computing centers and cloud providers. Okay, so that's something that we will learn to make the difference, and then hopefully see some examples of this, either in Mexico or here in Europe, so that you can see both differences. Just to have a look at the kind of things that we have to consider, the technical aspects of high performance computing in general. It's the type of processors they use, and there is a huge market with respect to this. If you are like planning your professional career, these are two elements that you have to consider to have ideas. And if you are planning to do internships or whatever, it would be very important that you approach a company that has access to this type of processors, so that you can see in real problems and acquire experience in this kind of problems, so that you can have a good a professional market to access in your life. So the idea is that, well, this evolves very fast. This slide is from 2018, where this famous laboratory in Puebla was established, but now things are evolving very fast. And so the idea is how many petaflops of cycles your processors can deal with. Okay, and in the HPC arena, there is globally in the world a kind of competition to see which are the centers that have the most number of petaflops of cycles running, okay, and what they are able to run. The most important ones are in China, but there are others that are competitive and that are have quite important capacity in their centers. So the flops, and as I said, all the question is not to have. It's like having a powerful car. Okay, so let's say that that you have these Elon Musk cars. If you are running the car at 20 kilometers per hour, well, it's good that the car can run for whatever. I mean, you're just going like a horse, no? So the idea is not having this power accessible, but it's to be able to use as best as possible the resources available in order to deploy algorithms. And this is what we're going to learn here, okay? How do I best use my resources in order to run a specific algorithm or specific algorithms. Then, of course, there is a workflow that shows how do we use this type of machines. Of course, you do not remember, but you certainly were born when personal computers were there, and nobody told you, you know, in order to use your computer, you have to turn it on, and then you do this. This is something that you learn like empirically and directly, and well, but anyway, there is a workflow in order to use different architectures. So normally the workflow includes three main aspects. There is one aspect which refers to the type of hardware that you can access to. Then the number of tiers that can be used in order to deal with the data, and then the strategy that you use in order to access to the computing cycles. And then, of course, the way you connect to the data center. Of course, you can imagine that you do not have to be physically in the data, I mean, the HPC center in order to run your processes. You can do it at distance, but you need to have the right connections in order to be able to use it correctly. I know that there is a course in your syllabus. It's parallel computing, and in parallel computing, I believe that you connect to the LNS in order to run the exercises. And well, now you cannot visit the center, but there is a special connection to the LNS in order to run your processes. So this could be easily seen, but if there is no possibility to see that, I believe that we will have access even remotely to some center here in Europe, and so that you can see even at distance how this works and how you can use these kind of things and see the workflow in real. Now, the question then is, how are resources for scale data management tasks delivered? And this is where these different architectures and these different philosophies of accessing computing resources come up. The one that we are going to study here is, of course, the cloud that has a reference architecture. I will not go into the details today because today it's just a kind of overview of all the things that are touched in this course. But anyway, there is a reference architecture, and there is a specific philosophy associated to the way you deliver all this CPU and this storage support to clients, okay? And the only thing to retain today is that the very objective of the cloud is to provide the illusion of infinite resources, okay? So we users of the cloud have the impression that we have access to, in an infinite manner, to computing, storage, and main memory resources without having to buy them, okay, all of them. because there is a model, a business model, which is called fine-grained billing, which says that you only pay what you consume. So another aspect to retain about the cloud is that it promotes a dynamically scalable way of accessing to resources, and that these resources are accessed in a virtualized manner. So one of the things that we really will really study in this course is how to virtualize, okay, how to deliver, well, of course, how to access and how to create virtual spaces that use the cloud in order to deploy our solutions, okay? And this is, again, one aspect, a very important aspect of a profile of a computing engineer today. Any company, any vendor, leading vendor in the world asks for proficiency about this virtualization experience. Okay, so it is very important that you make sure that you are able to prepare virtualized environments in order where you deploy solutions. Okay. So if you want, there is something that you, there is a checkbox somewhere in your notebooks. Please write there, and then at the middle of the course and at the end of the course, make sure that you really control this smoothly. Okay. And then, of course, the way, because of this billing model, the idea is that the customers of the cloud rent computing capacity. Okay, so that's what we do. We rent this, and the cloud, in a very transparent manner, which is one of the main differences of using other type of solutions, let us organize any size of computing center in order to deploy our solutions. And then if we focus on data management, of course, many of the solutions running on the cloud are data centered. And so the idea of this course is to show you how to deploy data management solutions in this kind of infrastructure, which means how are you going to store it, how much, what are the guarantees that you are going to provide to the users of your data, and then which are the types of processes that are going to run upon your data, exploiting as much as possible in an optimum manner the computing resources that the cloud provides. Of course, we will also go through vendors. This is a quite industrial situation. The real cloud providers are vendors, and there are leading vendors that you have to bear in mind, because these are the outmost cloud solutions that you can access to. Others are just trying to build cloud solutions, but really so cloud solutions that are real, that are there, that ensure guarantees, etc., are coming from these vendors. So they are just wrapping solutions that exist for a long time ago. So in fact, it goes back to the 60s where there were mainframes. So there's still the notion of mainframe, even in if it's organized in a different manner. And then you go up to many investors. Here is until 2014, but we will discuss later on how this cloud evolution timeline has dealt to important solutions. And then the last but not least, I just want to make sure, yes, I'm almost there. How to exploit such resources? It's like by having well-adapted programming models. So here in the course, we will address two main programming models parallel programming models. I will also use some sessions in order to explain that these are not the only models that we have, but at least they are the ones that are used in the for dealing with data. One is the one that focuses on a data flow strategy, which is the one that you have learned in data management systems. You have an execution plan where the nodes represent the operations that you are going to apply to a database in the case of DBMS, relational DBMS, and here we will see that it is applied to other kind of data. And then the control flow approach that we will also learn, and that is devoted rather to think about a program and determine how you can replicate the same function on top of different machines in order to parallelize your processes. So this looks like this. In the first case, you have this query plan that you already know from relational databases. You have many nodes associated to the same distributed data space and a master that controls all this. And then the idea is that every operator will run in parallel in different nodes, and the execution of all this is coordinated by a driver. And then in the other approach, you have a program, you have code, and the idea is that the functions, the same functions of the program are replicated in different nodes in order to parallelize the operation. But this grabs all this, okay? So here you do not see the details, just have the code and then you replicate all of it in different nodes. And these are the two main models that we are going to study in the course. Now the content is huge, big, but important. Okay, so this content, you have it already on the blackboard. It's in the described in the syllabus. So there will be 5 main topics. Today we're finishing the first one, which is having the overview of this. Do not get scared. There is a lot of things to do, but you are now almost computing engineers. So this is why it is challenging, okay? But it's very interesting. So we will start from the bottom to the top of the stack. We will deal with distributed management and storage techniques adapted to the cloud and to cluster-based architectures. Then we will go up to the processing of the data. Once we have had stored it, then we will study how to process it at scale under the different programming models that I have described, even with one that is very popular today, that it's based on matrices, which is TensorFlow. You have probably heard about it. It comes from Google. And then the third thing is that we, as I said, we have to learn how to grab everything together in order to deploy our solutions on the cloud. So I will discuss different ecosystems for managing massive data and processing, particularly knowing how to virtualize, how to build containers, and how to deal with cloud brokers, which are the 3 main solutions that are out of the box in the world. And then we will discuss open perspectives and trends so that you know what is the open market and where to tackle in order to organize your professional career. The methodology is, in theory, we will have a content manager, the site and the blackboard. The communication is always on Slack. I have also a Google group in order to communicate with you all, and the course email is the one that is shown there. You have this information now on the blackboard, and starting from the next week, all this content will be there, so no need to try to write this on your notebooks. Now, evaluation, as I said, in my courses, there won't be exams. There will be rather cases that you have to develop, and that will be graded, okay? But the control is continuous. As in the other course, I will provide with control questions that you have to answer. I will ask a lot of reading, and again, we will either discuss the readings in class, or I will provide you with some quizzes. But again, not to grade you, but to make sure that you got the message of the papers, okay? And for the cases, there will be, there I will grade, there's a percentage of things, but you will see that it's construction. So you will do several deliveries, and then at some point you will wrap up the solution, and then you will get a grade. But that's the way we're going to work in this course. And then again, there's this diversity and inclusion statement. It is very important. So again, when you will have to prepare some reports or some delivery of the cases, I will point out some aspects of inclusive and diversity writing, and then about inclusive presentations. And then, of course, as I said, part of the diversity and inclusion is also accepting that if you do not want to adhere to this kind of challenge, you can decide not to do that with no impact in any perception that it will have with respect to your professional work. So let's, we are ready to start. I don't know if you have questions. Please open the mic if you do before we end the session.
Oh, no questions, doctor.
Very good. Again, remember that at some point, if you are thinking about something and that something comes up, please feel free to write on Slack. And
Okay.
as I said, okay, and as I said, as soon as we finish, as the session in the laboratory, it will be on the site on YouTube, and then I believe that the sessions recorded are also stored here on the Blackboard. So, and then yes, for the next time, that's something that I will write on by mail so that you can have all the specifications. I will ask you to read 2 or 3 documents. So I will have the time to tell you how to read and how to prepare your readings, and this you will receive in the next days on the mail, so that you can have time to prepare all this. You will see it's not a lot, but it's important that you start reading in order also to open the discussion. So if there are no questions, we're going to end the session here. I'll see you tomorrow to start with storage aspects. And I wish you a nice Friday.
Thank you, doctor. See you tomorrow.
See you
Have
tomorrow.
a nice weekend.
Well, we're having a nice weekend tomorrow only.
Yeah.
Thank you, doctor. Have a nice day.
Don't skip the class.
Never.
Okay.